Dissonance is a word that means displeasing sounds. Sounds whose frequencies do not form small whole number ratios sound dissonant or bad when played together. So we're going to go back to our tone generator online. So we have 330 and 440 and 550 all sounded nice when played together. So let's find something that is not a nice whole number ratio with 440. So let's make this like 250. So 25 to 44 isn't a nice whole number ratio. So let's play those together and see how they sound. Okay, so not terribly great. Not terribly great. I'm getting this little interference again. I'm going to have to reopen these, I think. Okay, so I'm going to play my 440 again. And then... Okay, so notice how that does not sound at all good together. Okay, they do not form a nice whole number ratio, so they do not sound good together. Now, there's a special kind of dissonance called beats. Beats are the periodic and repeating fluctuations heard in the intensity of a sound when two sound waves of very similar frequencies interfere with one another. The beat frequency refers to the rate at which the volume is heard to be oscillating from high to low volume. For example, if two complete cycles of high and low volumes are heard every second, the beat frequency is 2 Hertz. The beat frequency is always equal to the difference in frequency of the two notes that interfere to produce the beats. A piano tuner utilizes the phenomenon of beats to tune a piano string. Okay, so I'm going to show you a beat frequency using the 440 and the 444 Hertz. Okay, so we're playing 440 Hertz. Now, let's make this 444. Oh, sorry. I need to... I forgot. This is the 440. Now I've got to go to the other one. And we're going to make this 444. Now what you hear is a fluctuating sound that vibrates about 4 times per second because they are exactly 4 hertz apart in frequency. Now if I make this, now there'll be a little faster fluctuation if they're farther apart. Now if I made them if I make this 441 instead, you'll see a fluctuation of 1 every second. Now, how do piano tuners use that? They'll strike a tuning fork that is the tone that they want to tune the note to, and then they'll pluck the string on the piano, and if they hear that fluctuation, that beat frequency, that woo kind of thing, they'll know that the notes are out of tune, and they'll keep tuning it until they don't hear that beat frequency anymore. So what does it look like when we make a graph of this? So once again, I'm going to use the 440 Hertz frequency, and we have the equation for that already, and I'm going to use the 440. So this one is 2 pi times 444, or 888 pi is my B value. So here's my second equation, sine of 888 pi x. And I'm going to add those two together. So let's go to the calculator and see what that looks like. So I already have these two added together, so I'm just going to edit this one. 888. Now if you'll notice on your notes, I've given you a suggested period to, or suggested window settings to use, and the window settings have x max go to 0.05, I believe. Nope, I think it's 0.5. So let's go here. So 0.5. Okay, so now you see a really interesting pattern here. What you're seeing is a fluctuation, and I'm going to copy this and put it in my notes because it's easier to talk about when it's there. So what you're seeing here is a fluctuation of amplitude here. You're seeing almost like one sine cycle inside another. You can think about here that the amplitude is going like this, okay? And then there's another sine function kind of going up and down within it. So we have a variation in amplitude, and it's in a very regular pattern. So that's why you're hearing this loud, soft, loud, soft. So here's the loud and then the soft, okay? So loud's at the peak, soft right here. So you're hearing loud, soft, fluctuation in amplitude. And it's because those two beats are very close to each other. And in particular, we're seeing 4 times a second that it would be going loud, soft. And so the graph actually shows you that. Now, one other thing that's kind of interesting with sound waves is you may have heard of noise-canceling headphones. In noise-canceling headphones, you put on the headphones and it's just completely silent. So how do they work? So let's think about what would make, if we were to add a sound to the 440 hertz sound, what could we add? What equation could we add to this first equation, sine of 880 pi x, so that the amplitude would end up being exactly 0? Okay, what would cancel out the sine wave completely? Well, no, remember, we're adding the y values. So if we can figure out a way to add 2 equations where the y values are just opposites of each other, the sound would completely cancel out. Well, you might think about it a minute. Okay, a sine wave that would be exactly opposite of this sine wave would just be negative sine of 880 pi x. So if we added a positive and a negative sine wave together, they should just cancel each other out. So let's edit this, change this to 880, and 880, and make this negative. Okay, notice there's nothing there. Here's the graph. The graph is exactly 0. So the way noise canceling headphones work is that the mechanism inside them generates a wave that is exactly the opposite of any sound wave that is input. So whatever is input, it generates a wave that is the opposite of it, so the two of them cancel each other out completely, which is kind of cool. So that would be the equation for canceling out sound completely. Okay, in our next video, then we're going to look at how sound waves relate to musical instruments.